So this week in Algebra 3, today we've got basic matrix operations. So we're going to learn all about matrices this week. Okay? We have to learn all about matrices this week so that next week we can solve systems of equations with matrices. Okay? Which, I hate to break it to you, solving a system of equations with matrices is the easiest of the methods, if you buy into the matrix operations that we're going to learn. Because the same process goes for any size system. 2 by 2, 3 by 3, 4 by 4, 98 by 98. It's all done exactly the same way. Okay? And so, and it's super easy. It's like 2 steps and done. Okay? And so that's the nice part. So today we're going to do the basic stuff. We're going to get all of the operations and we're going to learn about matrices again. I think I did them in L2. Yes? No? Maybe? Maybe you saw them and maybe you've seen them, maybe you haven't. Either way, we're going to spend time today learning all about them. Okay? Then, tomorrow, nothing other than make sure you get your significant other something nice, preferably not candy-wise, because, you know, candy just makes it go right to the hips. Then Wednesday, we're going to do matrix multiplication. We're going to multiply 2 matrices together. Then Thursday, we're going to have inverses and determinants of matrices. Okay? So Thursday is going to be an important day. Then Friday of this week, we're going to have school. Teachers have an in-service day, so you guys don't have to come to school. So Friday is just a hey, great, grand, wonderful day. And so we don't have a quiz or a test this week. Okay? So there's that. And then next week, Monday, I will not be here, but there will be a video for you to watch in class next week, Monday, on starting how to solve systems of equations with me. And then fix that for the following next week, Wednesday, and then we'll review. And then the 24th, so not this week, Friday, but the following Friday, the 24th, is when we are going to have our Unit 6. So that's the next 2 weeks here in the algebra trace. Okay? All right, so there's going to be a lot of stuff to write down off of this first slide. And then after that, then it gets much easier. But I gotta get you into thinking about matrices first, which is why I covered it up. Okay? So I'm gonna give you a couple of minutes to write all this stuff down. And then I'm gonna go through it because I think that way you pay attention more to the words coming out of my mouth than trying to write and listen at the same time. All right. So, a matrix is a rectangular arrangement of numbers. Okay? And it's organized into rows and columns. Rows go horizontally. Columns go vertically. It's kind of like an Excel spreadsheet. Okay? Rows and columns. Rows by columns, rows by columns, rows by columns. Okay? Okay? So, a matrix is named with a capital letter. So you've got 26 choices for the name of your matrix. Okay? But then the matrix is defined by its size. So this matrix here, matrix A, is a 2 by 3 matrix. The reason it's a 2 by 3 matrix is because the size of a matrix always goes off of rows by columns. It's always rows by columns on the sides. That, ladies and gentlemen, is the #1 rule, and really the only rule. It's really not, but it's the #1 rule matrices. Everything that you do in a matrix is going to be rows by columns. Okay? Rows by columns. Everything that you do in a matrix is always rows first, then columns. Especially when we get into Wednesday. Wednesday's big time rows by columns. Okay? So, the individual parts, the individual numbers of a matrix are called elements. And those elements have their own address. Just like you have your own address, which is different than my address, which is different than your neighbor's address, either here in the room or actually at home. Your neighbor has a different address than you. Okay? The different elements have a different address. So for instance here, 3 shows up here. Well, that shows up in row 1, column 1. So its address would be capital A, because that's what matrix you're looking at. 1, 1, row 1, column 1. 8, 2, 3 over here signifies that we are going into matrix A. We're looking at row 2, column 3. Okay. So those addresses are important. Okay. Now, the reason that the addresses are so important is, again, on Wednesday, when we're multiplying matrices, if we're multiplying a matrix, you're going to take, so like if we had address A23, that would be the second row of the first matrix that you're multiplying times the third column on the second matrix that you're multiplying. Okay? So those addresses and those elements are extremely important. Okay? Again, rows by columns. Always rows, always columns. Rows by columns. Okay? Questions on the basic of the makeup of a matrix. Okay? Always rectangle, always has brackets. And yes, can't just be straight lines there. Has to be brackets. Straight lines on the side mean something different, and we're going to learn that on Thursday. Okay? So it has to be brackets on the side of an actual matrix. Okay? Okay? No, every element spot, every address, if you will, is filled in a matrix. You can't just have a matrix that looks like that. Okay? You have to have every element filled in a matrix. Okay? Okay? So, we can do different operations with matrices. We can add them. We can subtract them. We can multiply them by a number. We can, later on Wednesday, we're going to multiply matrices together. Divide matrices. Okay? We can do all of that following some certain rules. Okay? So, rule number 2 of matrices is that if you are going to add or subtract them, they have to be exactly the same size. If they are not exactly the same size, there is no possible way that you can add or subtract them. Okay? They have to be the same size. If they're not, done. Literally done. Can't do it. Not possible. Not no solution, not zero, not possible. If they're not the same size. Okay? So the majority of the time, when you get to a matrix problem, the first thing that you're going to do, or the first thing that I'm going to ask you to do, is determine what the dimensions of what you're doing are. Okay? So this first one has 2 rows. Here's 1 row, here's 2 rows, and it has 2 columns. So this is a 2 by 2 matrix. The second one has 2 rows and 2 columns, so it is also a 2 by 2 matrix. They are the same size. So we can add and subtract them. If they weren't the same size, we would be done at this step. So being that they are the same size, we simply just add the corresponding elements together. So 4 gets added to 2 because they're in the same address, just on different matrices. 0 gets added to 7. -6 gets added to -1, and 2 gets added to 5, -5. Excuse me. So the resulting matrix here is a 2 by 2 matrix. Now, when you are reading off a matrix to somebody else, first off, you tell the size of that matrix. So the person in their mind knows where to stop writing in the first row. Okay? And then you read it left to right, taking a brief pause after each row. So this is a 2 by 2 matrix, 6, 7, -7, -3. Left to right, top to bottom, just like you were reading a book. Okay? Take a pause after each row. Questions on that? And that, I'm not going to lie, you want it to be more. I get it. You know, you're in a Linsmeyer math class, and Linsmeyer always makes things be more difficult than they really are. Or he drops, what does he do? He drops like, yeah, this is pretty easy, but then the next problem is just brutal. Not in this case. It is literally, if they're the same size, you add the corresponding elements. Or subtract the corresponding elements. That's it. Okay? If they're not the same size, can't do it. You're done. Okay? With that being said, you try this one. First question is, are they the same size? Visually, they look to be exactly the same. Mathematically, they are both 2 by 2 matrices, which is going to result in a 2 by 2 matrix itself. Okay? So in my first element, row 1, column 1, I would have 3 minus -3. Then I would have -5 minus 0. Then I would have 10 minus -2. Then I would have -4 minus 4. And that would give me, as a resulting 2 by 2 matrix, that would give me 6, -5, 12, -8. Agree. Speak now, forever hold your peace. Good. Okay. You look like you were going to gonna ask something.
No, yeah.
Simple subtraction. It kills you every time. Yep. And then she copied you, so then she got it wrong. And yep, blondes, I tell you. Okay, fine. Thank you. Thank you for allowing me to continue. Yep. Okay. Now, NTC in the past has loved this kind of a problem. Okay? They love this style of problem for the final that you have to take sometime in a couple of months. Okay? Now, this one is basically the same as what we just did. So it's saying here that -2 plus -3 is -5. Is that true? Yeah, -2 plus -3 is -5. Then it's saying 1 plus 6 is y. So what's y? 7. Then it's saying x plus 7 is -2. So what's x? -9. Are there any other variables that we have to solve for? No. So that problem's done. It likes, for some reason, whoever designed this course over at the NTC loves these style of problems. Like one year there was 3 of them on the top. I'm like, that's kind of overkill. I mean, for me to blow the old math teacher just with a master's degree, you know. Okay? Good with that? Adding and subtracting can handle it? Okay. All right. The next concept that we have to talk about is scalar multiplication. Now, scalar multiplication in a matrix is different than matrix multiplication, which we'll learn on Wednesday. Okay? Scalar multiplication is just like the distributive property, but it's in a matrix. Okay? So you have a number, a single solitary number out in front of a matrix. And all that has to happen, or all that happens with that, is that number gets multiplied into every single element within that matrix. So the result here would be -3 times 3 is -9. -3 times -2 is 6. -3 times 1 is -3. -3 times -10 is 30. So the resulting matrix here is a 2 by 2 matrix. -9, 6. -3, 30. Adding, subtracting, and scalar multiplication do not change the size of a matrix. I'll say that again. Adding, subtracting, and scalar multiplication, the 3 concepts that we did today, do not change the size of a matrix. Thought I had one down here. Here's the purple. Okay. Now, sometimes they'll take it to the next level. NTC also loves, or used to love, this style of problem, where it's a crazy combo of scalar multiplication on the first one, and then adding or subtracting on the other one. Or they might take it double to the next level and do scalar multiplication on the first one, scalar multiplication on the second one, and then they add or subtract them in the other ones. Okay? Okay? You try this one. I'm going to let you try this one and see if you guys can handle it. I think you can.
So that would be 8, 12, -4 is 20.
Eight minus 6 is 2. 12 minus -4 is 16. -4 minus 1 is -5. 20 minus 5 is 50. So I get, as a result, the very end, this is my answer, the 2 by 2 matrix 216, -550. Agree? What's different on this one? Fractions. Does the process change, though? No, the process doesn't change. Still multiplying through by 1/4 on the first fraction, still multiplying through by 2 on the second fraction, and then combining that in the end of it. Go for it. So if I multiply in by 1/4, 8 times 1/4 is 2. -12 times 1/4 is -3. 0 times 1/4 is 0. 4 times 1/4 is 1. Still going to have addition. If I multiply the second equation, or the second matrix by 2, then I would have -6, 14, 2, and -4. And now I can add those two together. And when I add those two matrices together, because they're of the same size, 2 plus -6 is -4. -3 plus 14 is 11. 0 plus 2 is 2. 1 plus -4 is -3. So I get the 2 by 2 matrix -4, 11 to -. Agree? One last NTC's favorite type of problem equation. You got this one. Okay. You try that one now. So that would be 3/4 times -4 plus 3 equals x. 3/4 times -4 is -3. -3 plus 3 is 0. So x is 0. Then you've got 3/4 times y plus -4 equals 5. So there I would add 4 first. Then I would multiply by 4/3. Four thirds times 3/4 is 1. 9 times 4/3 is 12.
So I get y here is equal to 12.
Agree? 9 divided by 3 is 3 times 4 is 12. Okay? This week's worksheet is worksheet number 23. It's pink. You can now do the entire front side of it. Okay? So you have the front side of that worksheet that you can do.